All right, y'all. Today we're going to be talking about the chain rule. Okay, so the chain rule, it's another one like the product or the quotient rule where it's looking at a specific type of function. The specific function we're going to be dealing with is what we call a composite function. So a composite function is a function within another function. So to kind of start with this idea, we're going to be identifying our composite functions. Okay, so for each of these, we're going to identify f of x, which would be our function on the outside, and g of x, which would be our function on the inside. So what I'm looking for is this situation, f of g of x. So that's what I mean by composite function, a function within another function. Okay, so let's look at it. So we have y equals x squared plus 1. So x squared plus 1 would be our inside function. Square root of x would be our outside function. So we would say that f of x equals the square root of x, and g of x equals x squared plus 1. Okay, so if you remember this from pre-cal, your composite functions, if I take them apart, if I pull that inside piece out, then what I take out I have to replace with an x. Okay, so let's look at our next one. We have y equals sine of 6x. So my inside function would be 6x. My outside function would be sine of 6x. So f of x is equal to sine of x, and g of x is equal to 6x. All right, we have y equals 3x plus 2 to the 5th power. So that 3x plus 2 is my inside. My outside is this 5th power. So just like the square root, okay, my f of x, I just replace the inside with an x. So that would be equal to x to the 5th. G of x would just be that inside. All right, and last but not least, we have x plus tan of x squared. So my outside function is going to be all this. So f of x is equal to x plus tan of x. My inside function is right here. Just like so. Okay, so when I apply the actual chain rule, what I'm going to do is to derive this composite function, I'm going to derive the outside, leave the inside alone, and then multiply by the derivative of the inside. So the derivative of f of g of x, a composite function, we derive f, leave g plugged in the same, and then multiply by g prime. Okay. So this is a little bit weird, so we're going to kind of practice it. One of the things I do want you to note, as we saw up here, where sine of 6x, well, trig functions are a composite function because it's a function within another function. So all of our trig functions, technically, we can apply the chain rule. So like if I was deriving sine of some function u, then it would become cosine of u times u prime. Okay. And likewise for all of our other trig functions. So all of our trig functions are composite functions, and we're going to see that more moving forward. Okay, let's look at an actual example. So number one, we have y is equal to the square root of x squared plus 1. Okay, so first and foremost, before we do anything else, I'm going to go ahead and change this to something I can actually take the derivative of. So x squared plus 1 to the 1/2 power. Okay, so now to find my y prime, remember my outside function is this 1/2. My inside function is x squared plus 1. So I find the derivative of the outside. So 1/2 to the negative 1/2. So I derive the outside of the function first. The inside stays the same, x squared plus 1. Then I multiply by the derivative of the inside. Derivative of x squared plus 1 would be just 2x. And that's my answer. As always, we can be lazy and leave it like that. If we wanted to simplify it, though, 2 and 2 would cancel out. This would become 2x. Sorry, not 2x, just x. X over the square root of x squared plus 1. Just like that. Okay, let's look at another one. Number 2, we have y is equal to sine of 6x. So our inside function, 6x, outside function, sine. So y prime is equal to derivative of sine would be cosine. 6x stays the same. And then we multiply by the derivative of 6x would be 6. Okay, and that should be it. That one we don't even really have to simplify because it's already done. All right, let's look at 3. So y is equal to 3x plus 2 to the 5th. So outside function is, wrong color. Outside function is that 5th power. Inside function is that 3x plus 2. So y prime is equal to 5 comes down, so 5 parentheses to the 4th. Inside stays the same, 3x plus 2. And then we multiply by the inside. So multiply by derivative of 3x plus 2, which is just 3. Hey, hopefully starting to make a little bit of sense. I know it's still kind of weird and new, but let's look at 4. So 4, we have y equals x plus tan of x squared. Right, now last time I said we have an outside and inside function with this one, but really I'm only applying the chain rule for my second piece. I can derive the first part completely on my own. So y prime is equal to x would just become 1, and then plus is still plus. All right, now I'm going to apply my chain rule just to that tan of x squared. So tan is my outside, x squared is my inside. Derivative of tangent would be secant squared. X squared on the inside stays the same. And then the derivative of x squared would be 2x. So just like before when we were doing our product and quotient a couple of days ago, we can also apply these rules kind of separately. We don't have to, it's not like every time I see it, it's like, oh, product to the whole thing, quotient to the whole thing, chain rule to the whole thing. Can apply them to little individual pieces of the function. All right, number 5, we have f of x is equal to 3x plus 4 times 6x cubed minus 7 to the 4th. So we have multiplication going on. And then when I try to derive each of these, one of them is going to have chain rule. Okay, so we have our f and our g. So derivative of 3x plus 4 would be just 3. Derivative of 6x cubed minus 7 to the 4th. Well, I have my outside piece and I have my inside piece. So my outside piece, 4 parentheses to the 3rd. My inside piece stays the same, 6x cubed minus 7. And then I multiply by the derivative of the inside, which would be 18x squared. Okay, now I cross multiply. So f prime of x is equal to 3x plus 4 times 4, 6x cubed minus 7 to the 3rd times 18x squared plus 3 times 6x cubed minus 7 to the 4th. So yes, it's a mess, but we get to leave it as a big long mess. Okay. Number 6, we have 3x plus 4 over secant of 4x. So this one is a quotient rule. So we're doing our low d high. So low function on the bottom, high function on the top. Derivative of 3x plus 4 is just 3. Derivative of secant of 4x. Once again, outside function is secant. Inside function is 4x. So secant becomes secant tan. So this one's a bit weird because it's like I've doubled my function. Okay. Then my inside function stays the same in both. So secant of 4x, tan of 4x, and then I multiply just once, okay, because this whole first piece is the function, and then this whole second piece is just that derivative of the inside, so times 4. Okay, and then we are cross multiplying for our low d high. So remember, it's low times derivative of high minus high times derivative of low, all over low squared. So for g prime of x, it is 3 secant of 4x minus 4 times 3x plus 4 times secant of 4x tan of 4x all over secant of 4x squared. So just like the last one, big long mess. Okay. So the last two we're going to look at number 7 and number 8. Okay, so on 7, we have the square root of 4 minus 7x to the third. Okay, so this one's a little bit weird, okay, because I got a square root and I have a power. But remember, I can change that to a compound fractional power. So I can change this to be 4 minus 7x to the 3/2 power. Okay, that is legal. So once I do that, my outside function is that 3/2 power. My inside function is 4 minus 7x. So h prime of x is equal to 3/2 comes down. 4 minus 7x stays the same. This becomes 1/2 times -7. All right, and last but not least would be number 8. We have y is equal to cosine cubed of 2x. Okay, so to help us out first, I'm going to go ahead and rewrite this real quick because that cosine cubed just means the same as cosine of 2x cubed, like that. It means the same as cosine of 2x times cosine of 2x times cosine of 2x. So what I'm hoping you've noticed, okay, is not only do we have cosine of 2x, which is a composite function, but we also have cosine of 2x cubed, which is another composite function. So we essentially have this situation going on. We have that double nested composite function. So when we have this, what we're going to do is we're going to derive from outside in, applying that chain rule each time. So my furthest outside function is the cubed. My none of those colors really work. Let's change up our color. Sorry, y'all. Make this one like a little darker. There we go. So our furthest outside function is this cubed. Then we have our cosine, and then we have our 2x all the way on the inside. Okay, so first, once I find my y prime, I'm deriving my outside function. So my outside function is 3 parentheses squared. And then everything on the inside stays the same. So cosine and 2x. All right, then I multiply by the derivative of the inside. So now my inside is cosine of 2x. So now I'm deriving cosine of 2x. So to derive cosine of 2x, I derive the cosine. So negative sine. And then the inside of that function stays the same. So 2x is still 2x. Now I'm deriving by the inside of negative sine of 2x, which is just 2x. The derivative of 2x is 2. So what hopefully you should see is it's like we just worked our way in shell by shell to find our chain rule derivative. All right, that's all for today, y'all.